Good morning, everybody. It's Dr. Ellis here with a science assembly for Science Week. I was watching YouTube at half term and I came across a video by Steve Mould that got me to realise there's a massive money-making opportunity, and I'm going to share this with you today. This is Steve Mould's page on YouTube. He makes mainly like physics-based, short 15-minute videos, quite technical, but I'm a biologist and I can follow them reasonably well. Veritasium is probably one of the most popular science pages on YouTube. 11.6 million people subscribe to his channel. More people will watch it as well. He makes kind of like really high quality videos, again, that really get you thinking. Astron videos I also watch. I watch these at night when I'm falling asleep. He's got a really relaxing voice, so I get nice images of other planets viewed by space telescopes and probes and things, and he lulls me to sleep often. And then the Action Lab, who doesn't lull me to sleep. He makes short, often a bit quirky videos that again, really get you thinking. So back to this money-making idea, and I think it's more than that. It might be world-saving and even teeth-saving. Yes, teeth. I don't know which your favourite kind of Mars is, but we'll be kind of meeting both in this assembly on the topic of, wait for it, homochirality, which just means same-handedness. So what does chiral mean? A good example of chiral are our hands and feet. We have a left hand and a right hand, or I can say they are mirror images of each other. I can't pass a left hand off as a right. No matter how I rotate my left hand, I can't match my right. If I put my right foot in my left shoe, I can tell it doesn't feel right. So feet might be chiral, we have a left and a right, but socks are achiral. I can put either sock on either foot. There are sports socks that are chiral, where there is a different amount of support in different places to help prevent injury. So there is a left and a right. So an extra complication when you're trying to put those on your feet. The famous evolutionary biologist Richard Dawkins wears odd socks, as you can see in the picture. He states socks aren't chiral, so no need to match them. Inspired by this, I thought I'd give it a try, but couldn't bring myself to leave the house and quickly change into a matching pair. Screws are all right-handed, so they are achiral, hence the saying righty-tighty and lefty-loosey. I prefer clock to lock. As the thread of the screw is clockwise, I turn them clockwise to tighten them and anti-clockwise to loosen them. It would be chaos if the direction of the thread was random. You think all screws have a clockwise thread, but there are exceptions. Some mechanical watches have anti-clockwise screws that prevent cogs coming loose when they're turning. Hockey sticks are achiral or all right-handed. As you'll probably know, you can't use the back of a hockey stick when you're playing, as it's rounded and you're not allowed to. They don't allow left-handed mirror versions of hockey sticks for safety. The risk of striking an opponent with a follow-through would be much higher if games were played with left and right-handed hockey sticks. So the hockey governing body only allow right-handed hockey sticks to be used. So let's get to some science. Some molecules are chiral, so there is a right-handed form and a left-handed form. I can't rotate the one on the left in any way that will make it match the one on the right. Same for the hands. What is surprising is that living things only have left-handed versions of this molecule. This is an amino acid, a general picture of an amino acid, and they're all the left-handed form in every living thing on Earth. Sugars are also chiral. You'll have heard of glucose, I hope. This is glucose on the right hand side here. It's a 6-carbon sugar. It's C6H12O6. Americans call it dextrose, where dextro means right, and all sugars end in O's, so hence dextrose. The L form over here, well, the L stands for levo, and levo I always think of as just being left. This is the mirror image of the D form. So there's a D form of glucose, and there's an L form of glucose. And I can think of them as left-handed and right-handed. So D-glucose, the right-handed version, let's see how much it costs. It costs 0.3 pence per gram. Well, L-glucose costs 75 pounds per gram. Just for comparison, gold, that's very highly priced at the moment, costs 49 pence per gram. So this form, the L form of glucose, costs more than gold per gram. So L-glucose is 25,000 times more expensive than the D-glucose. Why? If we make these in a chemistry lab using organic chemistry techniques, you'll make about a 50-50 mix of both, in that each form of glucose has an equal chance of being made in chemical reactions. So this should cost the same if this was how sugar is made. The problem is, if we did make sugar in the chemistry method, both would cost 75 pounds per gram. So there must be a cheaper way in which we make sugar. Most of our sugar in the UK comes from this plant. It looks like a large parsnip. It's called sugar beet, and this swollen root is full of sugar made by plants in photosynthesis. So we get our sugar from plants. However, it's only ever the right-handed form, or a dextro form. Plants don't make sugar like chemists make sugar. The atoms of carbon, hydrogen and oxygen in glucose are added in a specific order to make glucose. This is an A-level diagram of reactions that take place in a chloroplast, where carbon dioxide enters the Calvin cycle. Get my pointer. There we go. So here's carbon dioxide. It enters the chloroplast, this green bit over here. That's where the chlorophyll is that makes plants green. So in comes carbon dioxide, and it enters this thing called the carbon cycle, the series of chemical reactions that take place. But these chemical reactions are controlled by enzymes, and the enzymes join the atoms in a specific order to make D-glucose. So the sugars that come out of the bottom, this will be glucose. And it's only ever the dextro form, or the D form, or the right-handed form of glucose that's ever made. So this is an enzyme. It's a protein with a complex 3D shape, like my feet have a complex 3D shape, and therefore works in a right-handed way to produce the right-handed form of glucose. So we have an enzyme here that only builds right-handed sugar, which itself is only made of left-handed amino acids. This is a big long chain of amino acids, and all those are left-handed. The code for this protein came from our DNA, and DNA is always right-handed. So we live in a world where some things are always right-handed and some things are always left-handed. And when they're always one or the other, we call that homochirality. So all sugars on Earth are naturally homochiral. There is only one form, and that's the right-handed form. The amazing thing about L-glucose, the very expensive form that we have made in labs, is that it tastes exactly the same as D-glucose, the cheap sugar made by plants, the right-handed version. However, we can't absorb L-glucose, the left-handed form. So we'd eat a sweet Mars bar and we'd gain no calories from the sugars in it. It would be the most amazing diet snack ever. We do have artificial sweeteners, but they often have an aftertaste and they don't give the results you'd want in baking and confectionery. You can't make caramel out of artificial sugars, for example. You can out of glucose, either L form or D form. You could even make jelly babies with L-glucose and you'd literally be cleaning your teeth as you chew them. There's no life on Earth can use the L-glucose. So the bacteria around my teeth will just be kind of washed off by my saliva as I eat them. They won't be able to feed on the sugar and make the acids that cause tooth decay. So if we can make L-glucose cheaply, there will be a massive market for it. Hence money to be made. So now for the other Mars, the planet. A scientist, Dr. Levin, wanted to find out if there was life on Mars, as we all do. The plan was to send some glucose on the Viking 1 lander. This is in 1976. And that glucose will be labelled with radioactive carbon. So we can just swap out the normal carbon atoms, carbon 12, in glucose, and we can pop in carbon 14 instead. They then sprinkled this on the Martian soil, and if life were present, for example bacteria, they'd use the glucose and release gases such as carbon dioxide. And as that carbon dioxide will be radioactive because it's come from radioactive glucose, it'd be detectable by having a Geiger counter, a little detector that can tell you how much radioactivity is present. They had to get hold of both right and left-handed glucose, though. We believe currently that it's just chance that we've evolved enzymes that make right-handed glucose on Earth. So all glucose on Earth is right-handed, and we think that's just down to a chance event. When life first started, it just happened to make right-handed glucose, and then that's been embedded and been passed on to all life that's evolved from that point. Martian microbes, the ones on Mars, might, by chance, if they exist, have evolved to use left-handed glucose. The experiment was not a success, as results were ambiguous or not clear. And quite frankly, we'd have heard about this if it did confirm that there was life on Mars. I'm just impressed that someone thought about chirality being a potential problem. They had to take both forms of glucose. It would have been a big mistake to just take the normal glucose that you can get, feed a plant some radioactive carbon dioxide, make it make some radioactive glucose and send that on a spacecraft all the way to Mars on a very expensive mission, only to then later think, we should have sent the other form of glucose as well because they might work in a different way than they do on Earth. Maybe that was obvious to the Americans though, because they do call it dextrose instead of glucose, and therefore maybe they're aware that dextrose means right-handed sugar. So making money from L-glucose. Let's have a look. Yeah, diets is the most obvious one. It tastes like sugar, it behaves like sugar, cakes will be the same, all kind of sweet treats will be the same, but there'll be no calories from sugar in those products. You still get calories from fat, this fat in chocolate, and therefore you get calories from that, but from the pure sugar, there'd be no calories, no available energy to you from it. Nothing can use L-glucose. So we could actually use it for carbon capture and storage. You might have heard of this, that we want to really lock away the carbon in the atmosphere. The carbon dioxide in the atmosphere is increasing. We're burning fossil fuels, releasing carbon dioxide into the atmosphere, and that's having a greenhouse effect. It's causing a warmer atmosphere. A warmer atmosphere causes greater, more intense weather events. It causes more flooding. It might cause ice caps to melt more, etc. And therefore we might lose land, coastal land, due to flooding. So if we could make plants that make L-glucose, we could just bury the glucose. Nothing could decompose it. You have to put it somewhere dry so it wouldn't dissolve, but you could lock away that carbon in a really kind of stable form. Now, currently we're talking about pumping carbon dioxide into old oil wells underground, but people worry about it leaking back out again. So this would be a really potentially good way of reversing global climate change. And my own personal favourite, that I could I need to clean my teeth, I'll eat a Jelly Baby. Yeah, just eat my special Jelly Baby that I get no energy from. The bacteria in my mouth can't use the sugar, and I'll be washing my teeth with my saliva as I chew on the Jelly Baby. And then I can switch to the normal, the D-glucose form of Jelly Baby when I want some fast energy for times when you need that. The good Jelly Babies for the release of fast energy, but you have to be careful to eat the right one to exist of different forms. So how can we make L-glucose? People have tried to do this. So we could refine the chemistry technique. It's just very difficult because you make both forms in equal quantities. It's very hard to then separate them from each other. It's just glucose and glucose. They look the same, they taste the same. I can't go in with tweezers. I'd have to have some way of like destroying the D-glucose to leave the L-glucose behind. So you could add bacteria that would then use the D-glucose as fuel, and then they'd release that carbon as carbon dioxide, and then you'd have your L-glucose left that you have to separate from the bacteria. It's messy, and people have tried it, and it's left us with a price of £75 per gram. So we have to really, really refine that technique to get the sugar down to a price that's usable. We could open a portal to a mirrorverse. In a mirrorverse, the plants will all make L-glucose. So if there was a mirror version of Earth, we could just trade with that alternate reality. We'll swap our plants for your plants. The trouble is, mirrorverses might not exist. I'm guessing they probably don't. And the opening of portal is still like science fiction, I'm afraid. I'd go for one of these last two, enzyme modification. What I'd do, I'd probably go back in time and study biochemistry at university, and then I'd specialise in proteomics, the science of protein shapes, not protein shakes, protein shapes. Enzymes are proteins, and I'll do genetics as well and try and create an enzyme by gene editing. That means I can make the carbon dioxide bind in a different way in photosynthesis to make the L-glucose. So that'd be my plan. Or you could just scrap plants altogether and try and make solar panels that absorb light energy and make left-handed glucose. So I'd have to have some kind of mechanism inside them where instead of the solar panels making electricity, I'd have some like chlorophyll in there that absorbs the light, and then I'd have a form of doing the Calvin cycle, but connect the carbon dioxide in a different way so that I made the L form of glucose. So that'd be my plan. And really, this is your problem, because I've had my time. There's always a snag. Yeah, it will cause diarrhea, I'm afraid. If you eat something that dissolves in water that you can't digest, like L-glucose, the left-handed form of glucose, it will prevent water being absorbed by your large intestine by osmosis. For those of you who know osmosis, year 9 up, I think. Too much water in your large intestines will give you your diarrhea. So eating this glucose might not be a good idea. If we traded plants from the mirrorverse, if that exists, nothing could eat them. We couldn't eat it. Insects couldn't eat the plants. They might just grow and grow and grow and take over the world and push out plants that can be eaten. So that might be a disaster. And it may be that it's just a brilliant idea, that right, yeah, let's grow these crops that can make the L form of glucose if we could get hold of them. But we'd have to chop down more forest to create land to grow these crops, to get the sugar to then bury, to lock away the carbon, and that would affect ecosystems all over. So yeah, there's always a snag, and we have to think things through before we do things. Things that sound a good idea are often not a good idea when you've thought them through a bit. But again, it'd be definitely worth testing, because it might be a solution to a problem that's very hard to fix. So back to the start. I still think that L-glucose is a real money maker. I just personally lack the ability to make it, but maybe you'll be the one that does. Or maybe you'll watch a science video and also be inspired. The video by Steve Mould at least inspired this assembly. So thanks very much for listening.